I'll now begin a series of videos where I review the concepts of work. And so, when it comes to engineering, not only chemical engineering, but even mechanical and civil engineering, when we talk about work, what we're really talking about is the transfer of energy between a system and its surroundings in a way that's not thermally driven, or in a way that doesn't depend on temperature directly. And so work is the transfer of energy between a system and its surroundings that is not thermally driven. And so when we talk about work, there's actually many different types of work that we could talk about. So different types of work. The main type of work that I want to focus on in these series of videos is called mechanical work. And so this is a type of work in which, or that causes the movement of a system boundary. So any work that moves a system boundary, or in other words, causes the system to change sizes. And so when we talk about mechanical work, here's a picture that I want you to have inside of your head. Okay? And so we're going to draw a piston cylinder system. But to simplify things, we're going to draw one that's on its side. So here's the piston part. And so between the end of the cylinder and the piston, we're going to have a gas. And here are the system boundaries of that gas. Alright, and so we'll call this the initial state. And in this initial state, the gas is just sitting idle, and the piston is sitting idle as well. And the distance between the left wall of the cylinder and the piston, we'll call that a distance of x1. Now let's say we add some work to the system somehow, or we add some mechanical work specifically. And because of this mechanical work, the gas is now expanding, or has now expanded. And so when the gas expands, it has to move the piston. And so instead of taking up a distance x1 between the wall of the cylinder and the piston, the gas now takes up a distance of x2. Okay? And so we'll call this state 2. Now, mechanical work occurred in this system, right? And so in order for the gas to push the piston away in order for it to expand, it needed to exert work onto the surroundings. And so as a result, in this scenario, when we describe the work is going to be negative, because by expanding, the gas had to transfer energy from itself, from the system, to the surroundings. So work is negative because energy is transferred from gas to surroundings. Alright? And so that's the general concept of work, or mechanical work. But we need to be a bit more quantitative when we describe this. And so, in general, when we talk about the mechanical work, we could say that the infinitesimal amount of mechanical work, either exerted onto or by the system, we're going to say that's going to be equal to the negative of some force exerted by the system times the displacement that that force causes. Alright, and so just to clarify, F here is the force exerted by system, and the x is displacement, or the dx is that displacement. And also take notice of that negative sign here as well. By convention, we say that this work is going to be negative, or we put a negative sign here. Okay? And so that's what dW mechanical work is. And so the mechanical work itself is going to be equal to the integral of dW mechanical. And so that's going to be the integral of f dx from x1 to x2. Okay? So that's what work mechanical is. But to get an idea, I'm still talking in somewhat vague terms, right? In order to actually calculate the work, we need to have an idea of what exactly the force exerted by the system is, or in our case, what the force exerted by the gas is. Okay? And to do that, we need to start thinking on the microscopic scale. Okay? Alright, and so as I said, in state 1 over here, the gas is idle and the piston is idle. Neither of them are moving. Alright? And so the reason that nothing is happening is because in state 1, the force exerted by the gas, which I'll call F gas, is equally balanced out by the force exerted by the atmosphere outside of the system. Right? And so I'm going to call that force atmosphere. And so force gas and force atmosphere are balanced. So the piston is not moving. Alright, and so let's illustrate this on the microscopic scale. Alright, and so what I'll draw is I'll kind of draw a segment of the piston like this. And on the left hand side of the piston we have our gas. Okay? And our gas, it's made up of molecules. And we could even just think of it as monatomic molecules. But we have a bunch of molecules on the left hand side. And they're moving in all different directions. They could be moving here, they could be moving there, moving here. And, if we have a molecule and it's trying to move to the right, but then when it runs into that piston, we could say that it bounces into that piston and bounces off of it. And so these little marks here are to signify collision. Okay? And so we have these gas molecules that are repeatedly bouncing off of this side of the piston. And when they hit the piston, they're essentially applying a force. Alright? And so when they hit the piston, there's some sort of force gas that they apply onto the piston here. Okay? And so I'll draw more molecules bouncing off the left-hand side. Alright, and so that's going on the left-hand side of the piston. On the right-hand side of the piston, we have our atmosphere. And our atmosphere, it's not a vacuum, it's most likely just air on the outside of the piston cylinder system. And that air is also going to be made up of molecules that are moving around. And those molecules, just like the gas molecules, those atmosphere molecules can also run into the piston and bounce off of it. And when they do, when they bounce off of the piston, they're also applying a force. And that force is going to be force atmosphere. And so, both of these things are happening. We have molecules on the left-hand side of the piston from the gas molecules hitting the piston, applying a force. On the right-hand side, we also have atmosphere molecules bouncing and hitting the piston and applying a force. And so in state 1, we said the system, we said that the force gas and the force atmosphere are balanced, and so that's why the piston isn't moving. And so likewise, mathematically, we could just say the force exerted by the gas is going to be equal to the force exerted by the atmosphere. Now, so we know this statement is true, but we still need to figure out what F gas is. And so when we think of F gas, essentially the molecules have some sort of energy, and they're bouncing into the face of the piston. Okay? All right, and so the way we could estimate the force exerted by the gas is by taking, the pressure of the gas and multiplying it by the cross-sectional area of the piston. And the reason we could do that is because we know for the gas in units, let's say we had a Pascal, we know that's going to be equal to newtons over meter squared, where newtons is a unit of force. All right, and so if we take newtons over meter squared and multiply it by an area, which is meter squared, in the end, we're just going to get newtons back out. Okay? So our force gas, we could say, is equal to the pressure of the gas times the cross-sectional area of the piston. Conversely, we could do the same sort of analysis for the atmosphere. We know that the atmosphere is characterized by some sort of pressure, PATM, and that these atmosphere molecules are acting against this face of the piston. So area of the piston. All right, and so in our relationship, we have P gas times area is equal to atmosphere times that same area. So these A parts cancel out, the areas, and what we're left with is that the pressure of the gas inside the cylinder is equal to the pressure of the atmosphere outside the cylinder. All right? And so that's why the gas in state 1 is idle. That's why it's static. And that's because the pressure on the inside of the cylinder is the same as the pressure on the outside of the cylinder. And the analysis that we did here, this is known as doing a force balance. Okay? All right, so we just analyzed the different forces that are acting on the piston, and from that we were able to get a relationship between the pressure of the gas and the pressure of the atmosphere. Okay? And so this is happening in state 1, but we know that in order for the gas to expand, it needs to exert some sort of work onto the surroundings. And so for that expansion to occur, so for the gas to expand to state 2, this gas needs to overcome the force of the atmosphere acting this way, right? So for the gas to expand, it needs to have a force that's greater, or that acts against the force of the atmosphere. So gas needs to act against force exerted by atmosphere. Okay? Alright, and so that's how we should think of the mechanical work, is that for the gas to expand, it needs to overcome the force of the atmosphere. Alright? Some other things I want to mention when it comes to mechanical work is if the displacement of the piston, if you will, is greater in state 2 than in state 1, this is going to be known as expansion. The system is expanding. And in that case, our mechanical work is going to be less than 0, because in order to expand, energy from the system has to be transferred to the surroundings. And so energy is transferred from gas to surroundings. On the opposite end of the spectrum, if x2 is less than x1, that means we would have compression going on. And as a result, our mechanical work would be greater than 0 because the energy would be transferred from the surroundings to the system. Or the surroundings would have to do work on the gas. Surroundings to gas.